I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology in the subject of Quantum Mechanics 2 with a course code PHY 313. We are at the lecture number 15 and the topic is spherical harmonics. In case of angular momentum, we know that the components of angular momentum do not commute. That means that if we calculate the commutator of any two components of angular momentum, for example Lx and Ly, that is not equal to 0, and so is the case for any other two components. The reason is the uncertainty between the components of the angular momentum, that the measured values of any two components of the angular momentum are uncertain and they cannot be simultaneously measured with 100% accuracy. Now what we do is to calculate rather the values of the square of the angular momentum and any other component. They certainly commute and their values are certain. Therefore they will also have common eigenfunctions. So this is the thing we want to do. But the next thing is to do it in which coordinates. For example, we can do it in Cartesian coordinates, but the problem with the Cartesian coordinates is this: they are rectangular, they are straight lines, and they do not fit to the situation and to the problem, which is inherently spherical, because we are talking about the angular momentum. So what we have to do is to shift towards the spherical coordinates, and shifting to the spherical coordinate or transforming to the spherical coordinates also help us in calculational way. This helps us in reducing the number of independent coordinates. We will see that when we will go towards the spherical coordinates, then our wave functions of L square and L, that is the orbital angular momentum square and orbital angular momentum, are independent of the radial component, and this will reduce one of the components, one of the independent coordinates, and will be easy to calculate. And the next important point is that these spherical coordinates will give us eigenfunctions which we will call them spherical harmonics, and these spherical harmonics are also important in many branches of physics besides the quantum mechanics. So in today's lecture we will talk in detail about how to calculate these spherical harmonics. So let's start. First of all, we will go towards contents, and I will show you that this lecture is divided into different parts, different components, and the first part of this lecture is about reminding you how to calculate the common eigenfunctions of orbital angular momentum L square and angular momentum Z component of the angular momentum Lz. Remember that we are not talking about here the total angular momentum, and there is a reason that why I have chosen to talk about only the orbital angular momentum. And this reason is, since in spin angular momentum the spin of the particle or a system can take integral and non-integral values, half integral values, and they almost its values are fixed and eigenfunctions are fixed, so it is not very interesting to talk about the spin angular momentum. Therefore we choose to develop the theory of common eigenfunctions, or to develop the spherical harmonics for the orbital angular momentum only. Therefore in this lecture we will talk about only the common eigenfunctions of orbital angular momentum, and we will call these common eigenfunctions, the spherical harmonics, because we will go towards the spherical coordinates. We will do all the calculations in spherical coordinates, and therefore in spherical coordinates these eigenfunctions will be called spherical harmonics. And harmonics, you can see that in orbital angular momentum we will have many possible values. That's why we call them harmonics. And since we are doing all the calculations in spherical coordinates, therefore we will call them spherical harmonics. Okay, but before doing this, it is important to revise that how we can get the common eigenfunctions of orbital angular momentum L square and Lz, and this is the first part of the lecture. So eigenvalues of orbital angular momentum will have they will have common eigenfunctions. The first point is that they will have common eigenfunctions because L square and Lz commute. By this I mean that if I take the commutation relation of L square z and Lz and calculate this commutation relation, then this is equal to 0. So they commute. So since they commute, therefore we have theorem in quantum mechanics that if any two operators commute, then its eigenfunctions are common. They have a common eigenfunctions. So we will be talking about the eigenfunctions of L square and Lz. So if I calculate their commutator, this will be equal to 0. That's why we have the common eigenfunctions for L square and Lz. So the first point is that they have L square and Lz have common eigenfunctions because they commute. Okay, so how we can calculate the common eigenfunctions of L square and Lz? There are basically two techniques, and in this lecture we will in detail talk about only the first technique, but first of all let me give you the details of both of these techniques for calculating the common eigenfunctions. As I said, there are two techniques. In the first technique is to solve the following equations, to solve these two equations. In these two equations, which we have derived already in the previous lecture, you can see that the L square is acting on this phi Lm. This phi Lm is a wave function on which this L square acts, and this is the eigenfunction of L square. You can see that when L square acts on phi Lm, then it gives us phi Lm back. So this is the definition of eigenfunction, that the function is reproduced after an operator action on it, it is reproduced again, accompanied with some constant. You can see here some constant values, that is L into L plus 1. This formula we have already derived, h bar square L into L plus 1. So these are called the eigenvalues. So this is the eigenvalue and this is the eigenfunction, and this is the eigenfunction of L square. But as we know that L square commutes with the Lz, and this so they will have common eigenfunctions. So this phi Lm is also the eigenfunction of Lz. So when Lz acts on the phi Lm, where L and M are two indices, by the way, L represents the orbital angular momentum and M represents the magnetic number, and L represents the orbital number. So these are the two indices representing the z component and the total square of the angular momentum. So this L is connected with the L square and this M is connected with the Lz. So it's simple to remember that L is connected with the L square and M index is connected with the Lz. Since they have common eigenfunction, therefore we have two indices over here. So you can see here that when L square acts on the phi Lm, the eigenvalue is L into L plus 1. That's why this L is represented in the index. And when Lz acts on the phi Lm, we have eigenvalue M. That's why M is here represented in the index. So in phi Lm there are two indices. These indices are actually denoting, they are describing that this phi has two ingredients inside it. One is related to the L square, and that is represented by the small l index, and another is represented by M, and this is connected to the Lz. Okay, so if we solve these two equations, this is the technique. But in terms of spherical coordinates, what we will get phi Lm. So what do we mean by solving these two equations? By solving these two equations, we mean to getting the values of phi Lm. But if we get these phi Lm in spherical coordinates, we call them spherical harmonics. So this is the first technique, and this is the technique we will apply in today's lecture, and we will learn. So to give you the quicker version of today's lecture, I will simply say that what we are going to learn is to transform this phi Lm into spherical coordinates, and then transform L square into spherical coordinates, and then act with the spherical L square on phi Lm and get something over here, and similarly transform Lz into spherical coordinates and act on phi Lm and get something over here. These will be called spherical harmonics. So this was the quicker version, but in detail we will see that how we can transform phi Lm into spherical coordinates and also L square into spherical coordinates, and then how we can solve these two equations to get the spherical harmonics. The second technique is to solve the following equation. So second technique is to go towards the ladder operators. You remember we constructed the ladder operators, and since the values of m actually run from minus L to plus L, and if we take the value of m maximum value, that is L, so this is the eigenfunction which is having a maximum value, and since L plus is a ladder operator, is kind of creation operator which takes the values of phi one step higher. So when we act with the L plus on phi LL, so since there is no higher values, then the result is 0. So you can imagine, you can recall that we have for example the minimum value of phi L over here, and the this is the minimum value, and maximum value is something over here. But when this L plus actually acts on these values, it takes us up there, and when it acts on this value, this is 0 because there is nothing here. It cannot go further. So therefore we can use this equation, that is L plus phi LL is equal to 0, because there is nothing higher than phi LL. This is a maximum value. So when if we solve this equation, and remaining eigenfunctions will be calculated from the action, from the repeated action of L plus and L minus. You can see in this sequence, this set, we have phi LL, phi L minus 1 and so on. So this is the maximum value. So we can go from here to here with the help of L plus, and we can have all the values, and these values are then called spherical harmonics. So by repeatedly applying the L minus on phi L and going downwards, solving this, getting phi L, and then repeatedly applying L minus on these values, we will be able to obtain the complete set of harmonics. So this is the second technique. So in first technique you have seen that shifting the operators and wave functions in spherical coordinates and solving those equations, or shifting the ladder operators in terms of spherical coordinates and then applying on to the maximum wave function values, and then using one of the operators to calculate the whole sequence. And you can see over here we can calculate all the values with the help of these ladder operators, either going from small values to high values, or alternatively you can also think of it that L minus acting on phi L minus equal to 0, and then going in the reverse direction, in this direction, going from here with the help of not L minus but L plus. So this L plus and L minus techniques are just the same, but it's only the difference of going from up to the down or from down to the up. Okay, so these are the two major techniques which we can use to calculate the common eigenfunctions of orbital angular momentum L square and the selected component, that is Z component of the orbital angular momentum, that is Lz. Okay, so this was the first part of our lecture, in which we have revised, we have recalled from our previous lectures that how we can calculate the common eigenfunctions of orbital angular momentum L square, Lz, L square and Lz. Now we move towards the second part of our lecture, and in this lecture I will again remind you how we can shift to the spherical coordinates. Usually it's very simple calculation, but difficult to visualize. So in today's lecture I will again quickly repeat that how spherical coordinates are connected to the Cartesian coordinates, and then how we can transform our wave functions and our operators in spherical coordinates. Okay, so as you know that if we are on a circular motion or we are in a rotational motion and in 2 dimensions, then we move on a circle. So for example, these are the Cartesian coordinates. Let's say call it this x, and let's say call it this y, and this is z. So these are the Cartesian or rectangular coordinates. These are straight lines, and unit vectors are along x and y and z directions. But if our situation is, or our problem at hand is spherical or rotational, then we shift to the spherical coordinates. And in spherical coordinates, then we will move towards some kind of a sphere. So we will have a radial component, let's say r, and it making angle theta, and there will be another angle over here, that is phi. So if we take the projection of this r here, let's say call it rho, and this rho making an angle with the z component is called phi. So we are basically shifting from x, y and z to r, theta and phi. So these are the Cartesian coordinates, and these are the spherical coordinates, and there is connection between them, there is a relationship between them, and this relationship is it is convenient to work with spherical coordinates, and in following way, that x is equal to r sine theta cos phi. So this is this you can derive by yourself and from this geometry. At the moment, just I have given you the hint. It's a very elementary calculation. You can find in any book, and you can see that x is equal to r sine theta cos phi. And quickly just telling you how you can do this, you see in this diagram we have r, that is radial vector, and then we have theta, and there is a projection. So projection is perpendicular component is r sine theta, and then we have this projection making an angle with z component cos phi. That's why x is equal to r sine theta cos phi, and y is equal to r sine theta sin phi, because in this projection we take the perpendicular component. In this case, we take the horizontal component of this angle phi, and here we take the perpendicular component, and z is equal to r cos theta, because in this case we don't take projection, but we take that z is on z. So therefore, so this is the kind of dictionary or transformation going from the Cartesian coordinates on the left and spherical coordinates on the right. Okay, so after reminding you that what are the spherical coordinates and how you can move from Cartesian coordinates to the spherical coordinates, now we see that how our operators can be shifted, can be transformed in spherical coordinates. So Cartesian components of angular momentum then become so this is the Lx relation for the Lx, which is equal to I h bar sine phi del theta, and you can see it is a very important point that it is independent of r. There is no r in here. We have theta and phi. It depends upon theta and phi. How you can calculate this Lx? It's a very simple calculation. You know that from our previous lecture, the Lx and Cartesian coordinate. So just use these equation on previous slide we have done, and use these equations to transform the Lx in Cartesian coordinates into the spherical coordinates. So this is left as an exercise for you, that kindly write Lx in Cartesian coordinates explicitly, and then use these equations to change it to the spherical coordinates. And similarly, the Ly, the y component of the angular momentum, is equal to I h bar minus cos phi and del by del theta. Again, an important point, you might have noticed that it is independent of r as well. And this was the one of the motivations, as I have already told you, that there are two big motivations to do the spherical coordinates or spherical harmonics. The first motivation is, since our geometry or problem's geometry is spherical, so we have to do the spherical coordinates calculations in spherical coordinates. And the second one is that it helps us in calculations as well, because there is no r, so we are now dealing with two coordinates, independent coordinates, rather than three. And for the z component, again you can see it's even nicer, because there is only one independent coordinate coming in, phi. So you have seen that now we have transformed our Cartesian components of the angular momentum into the spherical coordinates. So Lx in spherical coordinates and Ly and Lz all are now transformed into the spherical coordinates. Okay. So next thing is that we can also use the similar simple calculations to transform or shift our ladder operators equations from Cartesian to the spherical coordinates. And in this case, the Lx L plus, which is by definition equal to Lx plus iota I Ly. So L plus, that is the sort of accretion operator, this ladder operator will be of this form. This is again a simple calculation. I sketch for you that how you can do this calculation. So put in the value of Lx and put in the value of Ly, and when you put in the value of Lx over here in terms of Cartesian coordinates and the value of Ly in terms of Cartesian coordinates, and use the transformation equations between Cartesian and spherical coordinates, you can put in these transformation equations and do the calculations, and you will get this equation. And similarly, you can make the calculations for L minus as well. So L minus by definition is Lx minus I Ly, and what you do is to put in the value of Lx and Ly in terms of Cartesian coordinates, and then use the transformation equations to derive these two equations, these two terms, and you will see that few terms will cancel out, but these terms will remain. So in this way we have transformed the L plus and L minus from Cartesian coordinates into the spherical coordinates. And similarly, the square of the angular momentum in spherical coordinates will look like this. So this is the L square, and this nice relation you can derive for yourself, again using the value of L square in terms of the Cartesian coordinates, and then using the transformation equations to do this calculation. Okay, so in this section what we have do now, we have already learned that to transform the first of all to what are the Cartesian coordinates transformation equations related to the spherical coordinates, and then use these transformation equations to transform the operators in operators, normal operators in terms of Cartesian coordinates, and the ladder operators into the spherical coordinates. Okay. So we move towards the third part of our lecture, and in this third part we will talk about the rotation and normalization. We have done in the first part we have done the common eigenvalues, and then we have done the spherical coordinates, and in third part, before doing the actual calculation of eigenfunctions, we make two important points, that is rotation and normalization. So what do we mean by rotation and normalization, and why they are important? In the first part, this rotation point, I will tell you that why the Cartesian component, that is the radial component, is absent in the spherical coordinates, why the wave functions are independent of the radial component. And in the second part is the normalization, the second point. Normalization is a very important very important physical ingredient in any calculation, where we have to normalize our wave function. So I will show you that how we can normalize the wave function in spherical coordinates. Okay, so let's first go towards the first point, that is the rotation. As I told you, we are talking about the angular momentum operator, and we will see, and we have already seen, that the equations of the angular momentum in spherical coordinates are independent of r. When the wave functions of Lz and L square both are independent of r, they do not depend upon r, and therefore when coming to the spherical coordinates, we will now even replace our notation, and from phi, you remember phi Lm, we will go towards this notation, phi lm. This tells us that we are this y symbol is usually used for the spherical harmonics, where we are reminded, or we know that we are now working in the spherical coordinates, and this will be equal to phi lm theta phi, because our operators, as you have noticed already, are independent of the radial component, that is r. So we are left with only two coordinates, two independent coordinates, theta and phi, and this has to do something with the rotational problem, because we are talking about the angular momentum. There is rotation involved, and whenever rotation is involved, so this rotation is in the fixed circle or fixed orbit, and the radial component does not change. That's why we will not take it to account. To make it concrete, let's consider the angular momentum operator rotation, this rotation in the phi direction. So this delta is showing you that there is an infinitesimal rotation. This r is a rotational operator in phi direction, and we can write it slightly different from unity, that is 1 plus I delta phi dot L by h bar. So for simplicity, you can also think of that we are making the rotation in the z direction, or for example, think of electron which is moving around the z axis. So then we can only take the z component of this angular momentum, but for the moment consider this operator which is actually producing the rotation around any axis, maybe around z axis. And when this operator acts on any function f, it will produce the azimuthal displacement, and there is no r involved. So remember that this r is a function of this f is a function of r, and when this this rotational operator r acts on this function, which is a function of radial component, even then this delta r is here, is delta phi r. It will not change the radius, it will only create the rotation about the z axis. This is the point, that even the operator which acts on a function which is a function of r, it depends upon r, mind you, but this rotational operation is producing a motion about that axis, and r will not change. And this point helps us in calculating the spherical harmonics and making the calculations easier than the Cartesian components or the Cartesian coordinates. So that's the reason, one of the basic calculational reason, technical reason for which we do the spherical harmonics. So this was the point which I wanted to make before going to the actual calculations, that why the r component is radial component is absent, and it is connected with the rotational motion, because we are rotating something about an axis. Therefore it is not changing the radial component, and hence we have to deal with the two leftover rotation angles. And so generally speaking, when fr, which is a function of r theta phi, and when lz and l square operate on f, it is affected only through lz will affect it only through theta, and l square will affect it only through phi, and they will not affect r, and they will produce a motion about r, and that's why we can keep it constant, or we can treat it as constant. Okay, this was the first point, and the second point is important one, the normalization, and I would like to explain it in more detail because this normalization is very important, and in different branches of physics, not only in quantum mechanics, we often talk about this normalization process, so it's important to understand it. So by normalization we mean to scale it in a way that is convenient. So in this case we are talking about the wave function, so we would like to do this normalization on a sphere, probably on a sphere of a unit radius. So we want to normalize our wave functions on the unit radius, and when we do this on the unit radius, then you will see that our wave function will be normalized, and it will help us in calculation, and at the end the answers we will get, that will come in a nicer form. If we do not do this normalization, if we do not scale our wave function, what we will get, that our answers will be ugly, and we will have to make also an extra effort to make these calculations. So to remove both these points, that is not to make an extra effort and to make our answers nicer, we do this normalization, and it is taken over the surface of unit sphere. In our case, since we are talking about the angular momentum, there is a radial component absent, so we would like to make the r equal to 1, keep it constant since it's anyway constant, and normalize our wave function on a sphere. So how we do this? I would like to explain this with the help of the diagram or schematically, but before that, note that this ds, that is the area element on the surface of the sphere, is equal to a square d omega, and this d omega is actually the solid angle, and in this solid angle we are normalizing it. We will normalize this ds, and this a square is actually the radius, and this normal angle, solid angle d omega is equal to sine theta d theta d phi. Okay, so let's start normalizing it. So let's take the Cartesian coordinates first, x, y and z, and take the radial component, let's say call it a, and this angle between radial and z component, let's say call it theta, and also take the projection of this radial component over here, and the angle between this and axis, let's say call it x-axis, is let's say called phi, and then the next thing is to make an infinitesimal motion from this radius from here to here, and let's denote this motion spherically as d theta, and similarly there will be a motion in its projection, and let's call it d phi. So if we have a component that the ds over here, as you can see, this will be equal to d theta, a d theta, this side here, and this makes it a rectangle, and this length element, a surface element ds, is equal to a squared sine theta d theta d phi, or let's call it the solid angle d phi. And our purpose would be to integrate this d phi, and this will be equal to 4 pi, which is the volume of because since we are integration on a 3 surface, we are integrating on a unit sphere, and this is equal to the 4 pi. And if we make the projection, in this projection again you can see this is the a sine theta. So what we are doing is to normalize our wave functions, as to whenever we will write a wave function, we will write it in a way on this unit sphere that the answers bringing in from this integral 4 pi are cancels out, and we get the nicer answers. Answers looking nice. Otherwise we will get always these 4 pi factors. If we do not normalize this, we will get these factors in our final answers, which are not very nice, and also we will have to make extra efforts in calculations. Okay, so what we can do now is to go towards the normalization calculation, and as you know that if we integrate over d omega in all directions, this integral will be in 2 components. This is integral on d phi and d theta, and d theta integral can be simplified in this way. You can think of it that how sine theta could be put equal to d cos theta, and these limits will change as well. And if we do this two integrals, this is equal to 4 pi steradians, where steradians are the angle, are the units for the solid angle. So now we can normalize using this integral or this information. We can normalize our wave function, and this normalization is achieved in this way. You can see now we are putting in d omega over here, and we have constructed d omega as well, and these are the spherical harmonics, and 4 pi is the limit. And if we integrate this, putting this equal to 1, this is normalization. So whatever we will get from y, from spherical harmonics in this equation, will be cancelled out with the d omega, these factors, and we will get at the end equal to 1. So the eigenfunction equations for the Lz will be equal to, and in this way we can simply put it in equal to this. Okay, so far in the second part we have I have shown you the 2 important points about the normalization and how we can normalize our wave functions. Why it's important to normalize, because if we do not normalize we will get these cumbersome answers. and normalization is the scaling, and we will not make any mistakes in our calculations if we a priori normalize. Okay, so after this normalization, now we have reached to the final part of our lecture where we can calculate the eigenfunctions are spherical harmonics. So for this, let's first normalize our wave functions, and this normalized wave function, this technique for solution is to separate the variables in phi and theta, and we already know that now this phi m depends upon this capital phi m, this solution, this wave function depends upon the angle phi, and this theta depends upon the angle theta. So we have separated. So this is the technique for solution, that you separate your dependence of wave function on coordinates. So phi depends upon now theta phi, and theta depends upon capital theta depends upon the coordinate theta. And then as we know that this is only about the motion about the z direction, this is the Lz part, so therefore we can write e raised to power im phi, because phi m is equal to this, because if you put it back into this equation over here, you remember that this is the operator for the z component, del by del phi, and when it acts on a while m, so m will bring down m over here. So this was the very formal general equation, general solution for the z component acting on the spherical harmonics. And here you can see that this is the explicit form in terms of the this exponential function. We have 1 over 2 pi under root e raised to power im phi, and when we put it over here, we can solve these spherical harmonics and theta will be left out. So it means that we have only to solve for the orbital angular momentum, or L square, because theta will be left out. This we have already predicted, or we have solved, and we can normalize it again. So this phi m is normalized on d phi, because our wave functions are normalized. This y is normalized, so that's why phi m is also normalized. So we can calculate the values of this index m, because this will gives us the harmonics, and we require that phi is a single valuedness. So from the single valuedness we can calculate the values of the index m. So if we put phi equal to phi, because this is periodic, so after this period of 2 pi it will give us back our values. So we can write E m phi is equal to m because phi depends upon this angle, is periodic, so therefore this phi is also periodic, and this period is 2 pi, and you can see that this is equal to em 2 pi is equal to 1 after cancellation, and this gives us the integral values, because this equation will be only satisfied when we have m equal to plus minus 0 1 2 3, and that it has the integral values. And this is another test. Remember that these values m we got initially from another procedure, but now from the boundary values, or here, or from the single valuedness of the wave function, we have calculated that the m should be integer. Okay, so now we reach to the last part of our lecture where we will talk about solution. So in first part we talked about the common eigen functions, then we talked about the in second part spherical coordinates, in third part we made two important points about the normalization and rotational symmetry, or independence of the radial component, and then in the last part we are ready now to make the calculate the solution, or the calculate the spherical harmonics. For this we will go towards the Legendre polynomials, or we will get the Legendre polynomial. You know now that the final structure of our wave function is equal to this while m, these are the spherical harmonics, are equal to 1 over 2 pi e m phi theta, and this is already solved. This part we have to solve theta, and for this theta solution, if now remember, if you put this into you remember on our first slide I have shown you two equations for L square and Lz acting on phi and getting some eigenvalues. So now if we put our this wave function into that equation, and also the spherical the operators L square and Lz in spherical coordinates, and solve these equations, what we will get this equation over here. So this equation, you can see that this is for the theta, because this phi part is already solved. This theta is equal to this, and you can see that the structure of this is giving us the whole spectrum on values of L. That's why we call them spherical harmonics. And we can also solve this equation. This is also called a Legendre equation. So we can solve this Legendre equation conveniently by changing a variable to mu, putting cos theta is equal to mu, and if you do this, you see that this transformation is made, and this is useful for putting this limit, because mu is greater than or equal to -1 to +1, because it moves in these values. These are the maximum or minimum values. You can get this from cos theta, because this cos theta is a periodic one, is equal to mu, so this will be between -1 and +1. And then what we get, if we set m is equal to 0 and L into L plus 1 equal to lambda, what we get is this equation, which is called a Legendre equation, a simplified version of Legendre equation, which you have seen on the previous slide. This is a simplified in this case, because we have put m is equal to 0 and L into L plus 1 is equal to lambda, and now this is easy to solve this equation. And requirements for solving this is to the eigenvalue lambda must be of the form L into L plus 1, with L is greater than 0 and is an integer. And the second requirement is that this series solution contains finite number of terms, because it is a finite and it satisfies this L into L plus 1 condition. And if this is satisfied, what we get, this series solution nicely written into a Rodrigues formula. So this Rodrigues formula gave us a very nice compact form of this series. And the associated Legendre functions are also here. If we differentiate them m times, we will get these Legendre functions, and at the end, the final solution we get for these spherical harmonics are of this form. So in today's lecture, I hope you have learned that how to do these spherical harmonics. In the first part of the lecture, I reminded you about the common eigen functions of L square and Lz, and then it was important to solve this into spherical coordinates, because the geometry was spherical and it was convenient. And then we talked about the spherical coordinates, and then we talked about the normalization and radial component independence, and lastly we have solved these equations in terms of spherical coordinates and got this final equation, which is a series solution, and we see now the whole spectrum for our spherical harmonics. With this, I thank you all.